Welcome to your lab on reflection and refraction. Everything you need for this lab is right in front of me. Starting left to right, we've got a ruler, a few rubber bands, some straight pins in this clever ornamental pin cushion here, your square piece of plexiglass, some blank pieces of paper, a large piece of cardboard, the flat mirror, some tape, a block of wood, and a protractor, although I don't think you really need one this large. And if you're using electrical tape, you might want to have some scissors too. All right, now the purpose of this lab is to show you how light bends and reflects off of different objects. And the first object we're going to analyze is a mirror. So we're going to take a piece of paper and we're going to tape it down to the cardboard here. A few pre-cut pieces of tape. And then we're going to draw a line that I'm going to call line L across the width of the paper. And I'm going to do it in magic marker so you can see it, but I recommend you all do it in pencil so you can erase if you make a mistake. We're going to call that L, like that. And then I'm going to assemble part of my apparatus here by taking my mirror, my flat mirror, and attaching it to my block with a couple of rubber bands. Okay. I might only need one, but I think I'm going to stick a couple on here just in case, just to make this nice and level. Now the mirrors we sent your classes are silvered on the back. That means the silver part of the mirror, the actual reflecting edge, is on the back of the mirror. So when you line it up on your line, you want the back of the mirror to be in line with line L. All right? Now it doesn't have to actually touch the paper. It just has to be lined up with it. Now the next step is to take a straight pin, just stab myself with it, and a few centimeters, like about 4 or 5 or 6, in front of your mirror, you just stick it in the cardboard like that, through the paper, of course. Now, what I'm going to do is I'm going to look at the image of the pin in the mirror. And I'm going to put my ruler down on one side of the pin, and I'm going to sight along the ruler at the image in the mirror. Straight like that. Yeah, there we go. And I'm going to draw a line that lines up with that image. And I'll do the same thing on the other side, like this. All right, so I have two lines. Now for analysis, we're removing the mirror from the paper, and we continue these lines I just used, and we're sort of going to triangulate. Triangulate's a word meaning you're going to use two sides of a triangle to find a point. We're going to triangulate with these two lines out on the other side of line L to find where the image was of the pin. Now it's an imaginary pin, but that's where it was from the point of view of the side of the mirror. And then you're going to measure the distance that the image was from line L and the distance the actual pin was from line L. And then you're going to draw lines from where these lines intersect with line L to the original pin. And these lines right here will show you the path the light took when it bounced off the mirror back to the pin again. So it started from the pin and it came out, and then you saw it when it came out like that. All right? Now for the second half of the experiment, let me take our pin out. And we are going to test out Snell's law, invented by a guy named Snell, I guess. And we're going to tape down another piece of paper. And Snell's law says that given a certain type of substance which has an index of refraction, light will bend a certain way. All right? And we're going to test out the index of refraction of this square piece of plexiglass. First, we're going to put it down on the paper in the center, and we're going to trace out a square on the outside of this plexiglass very carefully here. Oops. Okay. And we're going to take the plexiglass off. And now, parallel to one edge of this square, I'm going to draw a straight line. That's not quite in the middle. And that straight line is going to be my guide line. And about 30 degrees, I think the first part of the experiment calls for 30 degrees from this line at this point right here. You see that? I'm going to draw another line that intersects with the square. And we're going to call this point B and that point A, but that's not important right now. Okay. Now I'm guessing that this is 30 degrees. It doesn't have to be 30 degrees for my demonstration. You'll have to use your protractor for that, but as you can see, mine's a little large, so we're just going to pass that along. Now you put your plexiglass back on here where it was before, so that the edge of it is at that point where these two lines come into it. And then on the other side, looking through the edge of the plexiglass, you're going to have to get down on your knees on the edge of the table and peek through the plexiglass and line up your ruler with the image of that line coming through the plexiglass. Oops. Okay. Now from my point of view right here, that looks like it's a continuation of that line. But when I lift the plexiglass aside and continue this line till it runs into the square, I can connect these two lines like this, and you'll see that it's a little bit crooked. And how crooked it is will determine the index of reflection of the plexiglass. And then you'll measure these angles, and you'll use Snell's law, the equation with Snell's law, to find the index of refraction of your plexiglass and do your analysis from there. And that's all there is to this lab.
Hi, and welcome to our lab on curved mirrors. In this experiment, you will become familiar with the properties of concave and convex mirrors. The first thing to do in this experiment is become familiar with our equipment. So starting on this side, we have the battery pack, 4-holder, 4 1.5 volt batteries, electrical tape, a penknife for stripping the ends of the wires on these 2 lamps if necessary. You want to cut off about 1/2 inch or a few centimeters of insulation in either case. Red, white, and black alligator clip wires, the 2 meter sticks, a ruler, a knife switch, small lens holder, a white card, the screen holder, which is this metal thing already attached, a large lens or mirror holder, 2 grooved wooden blocks, and finally the curved mirror itself. The first step in the laboratory is to assemble the lights. So to do this, we'll stick in the batteries, and you have to do this in the indicated direction. So mind the markings on the battery pack itself. Basically, they just go in an alternating pattern. And after you've done that, you can start to put the light bulbs together. You take these 2 lamps, you arrange them so that they're sort of close together but opposite, like this, and then you can twist the wires together and make that just about as far as you can, because that's very helpful, like this. And you do the same thing on the other side, like that. All right, and we didn't quite get it right on this side. There we go. Now what you want to do is to mount these light bulbs in this holder, somewhat off-center, and about the height of this little notch here where it takes a bend. And we will tape the wires in position, like that, so they cannot move away, like so. Okay, so they should be up and down and somewhat to one side. Now to complete the assembly, we attach the red clip wire to 1 pair of lights, and it's always important to make sure these copper things are twisted together so that current is flowing everywhere it should. Clip them together like that. Repeat the process by twisting these pairs together, the copper part that is, connecting that to a white lead. Then the red goes to the red. The white one goes to one of the terminals on the switch. And finally you close the circuit by means of the black wire. Black goes to black, and black goes to the free terminal. Now the switch must be open, of course, as a matter of good practice. Now if everything works, when I close the switch, the bulbs should light like so. And if they do not, please recheck your work. And when you're happy that they work, open the switch again. Now the next thing to do is to assemble the optical bench, as it's called. So you take the two blocks, take the meter stick, and mount the mirror in its holder, making sure not to get your fingerprints over the middle of the mirror like I am doing. This goes at one side with the concave or hollow side facing the center. And then you can mount the screen here. The card is lopsided so that the screen does not block the light hitting the mirror. You darken the room, find a light source like a window or a door that's cracked. You aim at the window or the light source. The light comes here, bounces off here, goes to the screen, and you slide the screen until you found the focus point, and you can measure that by means of whichever measuring device is convenient. After you've done that, you can then bring lights into the picture. You can scoot this a little bit closer, and then you want to mount these lights so that they are a certain distance away from the mirror, let's say, greater than the center of curvature, which would be about 30 centimeters or so. And the lights are near you, so you want to make sure that the card is away from you so that the light does not get blocked by the card. Make sure that there is a free path. And then you close the switch, the bulbs light, and you turn off the lights, of course, and then you slide this until you have obtained a proper focus on this side of the screen, because this is the light path. So that's how that one is done. And then finally, you repeat the procedure for a convex mirror, which you simply obtain by reversing this mirror. And then you locate the lamps at whatever distance you want. It's arbitrary. And then you are supposed to jiggle around this screen and try to find an image focused on it. And then the manual tells you how to proceed with the analysis. So I hope you have fun. Good day.
Welcome to your lab on convex lenses. This lab has almost all the same things you had in your last lab, except now we've got a convex lens instead of a mirror. To rehash what we have 2 meter sticks and 3 groove blocks that are going to be used to make an optical bench like I've already assembled here. You need the same little battery, wire, knife switch, and lights setup that you had in the last one, and if you were smart, you didn't take it apart last time, so you can save it for this one. Then you need the same screen holder, but now the screen is centered in the middle of the screen holder with our index card here. You need a ruler, and you need a convex lens and a convex lens holder, which I've already put together. Now, the first step of this experiment is very similar to the first step of the mirror one. You will be surprised how many similarities there are between this one and the last one. We put our lens at one end of our optical bench, which is 2 meters long, and our screen at the other. And then we darken the room. And just like before with the mirror one, you're going to aim your bench at some object off in that direction that has light, like an open door that has light to the hallway, or a window that's open, or any other light source that's more than a couple meters away in that direction. And the image is going to come through our lens and hit the screen. Now we'll move the screen up and down our optical bench until we get a sharp image in focus on this lens, what's coming through the lens. And then when it is in focus, you know that whatever point that the screen is at is your focal length of the lens. Now, knowing that, you should be able to get a clue as to what's going to happen a little later on, and you're going to record all this in your tables. Now, first we're going to move our lens to the midpoint and put our new light source at the other end, and we're going to repeat the experiment for a light source that's more than a couple focal lengths away, and then closer and closer and closer until we see all the different things that can happen. So we'll put our light source here at the end. We set our lens over here near the middle, and we've got our screen near the other end. All right. Now we turn on our lights. There they are. We turn off the lights in the room, and we move the screen again back and forth on this side of the lens until we get a sharp image of those two lights on the screen. And then you'll record in your table whether they're upside down or backwards or whatever. And then we repeat this experiment again, moving the lights closer and closer. And it's almost identically the same as the other one, except now you see your light sources are on the opposite side of the lens as your screen instead of on the same side as before. And that's all there is to this lab. You do your analysis according to the lab manual, and you got it made.
Hello, and welcome to our lab on static electricity. Electricity is nothing more than positive and negative electrical charges. Static electricity refers to charges which stay put. Electrical currents, on the other hand, are positive and negative charges in motion. During this experiment, you will be examining static charges. Strictly speaking, some currents will flow sometimes during this experiment, but that is only during the instance when you will be charging or discharging certain objects. Otherwise, the electricity will all the time be static, and you will be examining how positive and negative charges behave in close proximity to each other. To do this kind of investigation, you need the following equipment. Here we have a glass flask, and then next to it several rods. We have a polystyrene rod, which is transparent, and we find that something like this plastic thermometer casing works even better than this one does. So if you still have this, please use it. Then you have this white polyethylene rod, which feels kind of waxy and slippery. And then we have a rubber stopper, and this stopper is connected to a copper wire here. And this wire you will bend into shape during the experiment, but we've already inserted it to save time. Then we have a pith ball, which is this little green thing right here. And this pith ball is connected to a silk thread. And of course, here it's resting on 3 samples of cloth. Then finally, we have some pieces of aluminum foil, scissors, electrical tape, and a support apparatus. Now, to do this investigation, you need to build 2 devices. The first is the pith ball and its support. And this is very simply done. You simply take the pith ball and its thread, and you tie a nice big loop at the top end of the thread, and then you just hang it from this crossbar, like so, and you are done. Okay, so that's very simple. Now, the other thing you have to build, the electroscope, is a bit more complicated. To do this, you take the glass flask and then the rubber stopper, and through the rubber stopper you have threaded a very carefully bent piece of copper wire. So you see we have a contact loop at the top. It comes down, and then it bends to the side so it will not fall through the stopper hole. And then it comes out the bottom, and then we've bent it again to the side and put a little loop in it, like so. Okay, like that. And then we have finally put a piece of tape across the top to hold the thing in place. So that's one thing you have to do. The other thing you have to do that's a bit tricky is to cut the aluminum foil with the scissors. And we have already done this, and the results are 2 little pieces of foil, which I'll rest down here on this red cloth, and you can see that they're about 1 by 2 centimeters in size, and that the upper sides have little folds of aluminum foil. It's just been bent backwards just a tiny little bit, and this provides a hook by which you can hang these little pieces of foil. Okay, so to assemble the electroscope, you just take this assembly here, and then you carefully hang these 2 little pieces of foil on the electroscope, and you want to do this so that the short pieces of the foil are hanging on the outside. And it's just a tiny little bit of delicate work, and when you're finished, the pieces should sort of hang side by side with the short parts hanging on the outside, and they should be fairly free to flip-flop back and forth. And then you carefully lower the whole shebang into the flask, and you just push the cork down enough to hold things in place. It doesn't have to be tight by any stretch of the imagination. And that's your electroscope. Now, to investigate the behavior of these charges, all you have to do is select one of the rods, and then you charge it by rubbing it with one of the cloth samples, and this charging physically moves electrons around to produce a net negative or positive charge on the rod. And then, by bringing this charged rod close to the electroscope and to the pith ball, you can see a variety of interesting effects. For example, this one here. And when we zoom in on the electroscope, if you watch the leaves very carefully, I hope you will see that they also want to do a little bit of moving, like so. And so this lab will consist of experiments along these lines. So I hope you have fun. Goodbye.
Welcome to your lab on capacitors. Now actually we only have one capacitor in this lab. All the equipment right in front of me. Starting right to left, we have our clock or timer. We have various alligator clip wires as defined in our lab manual. We have our large 4-battery battery pack, each with AA batteries, 2 knife switches, your capacitor, 2 resistors, 10,000 and 15,000 ohm resistors, your lamp, and your multi-tester with your probe leads. All right? Now the first thing I'm going to do here is I'm going to plug my probe leads into my multi-tester. You'll notice on the multi-tester we have a little plus hole and a minus hole. Now plus is always associated with red, so I'm going to plug my red probe into the plus side and my black probe into the minus side. All right? And you notice there's several settings on the multi-tester. We have a few over here to measure voltage and a few over here to measure current, amperage. I think we only have one on this particular one though. And we have one for measuring resistance, but we won't use that one in this circuit. And then I'm going to hook up a red and black wire up to these probes so that I can clip this into the circuit later. I'm going to hook my red clip wire up to my red probe and black to black, just to be color coordinated, you know. And the next thing I want you to look at here is this capacitor. All right? Now you notice that this is sort of pinched in here. It's got a little groove that goes all the way around the body of the capacitor here. And that's to show you, as if you can't see these little plus signs that are also at this end of the capacitor, that this is the positive plate of the capacitor, and of course the other end is the negative plate. This particular capacitor has to be put in the circuit so that the positive side of the current, this side right here, is going through here, all right? So we don't mess up the capacitor. So the current has to flow from this side to this side, all right? And now this is built just like a battery, and we'll see how that works by charging it and discharging it here in just a second. Now, the first stage of the game is to build our circuit as it's constructed in your lab manual. I'm going to hook a red wire between the positive, that's the red wire coming from the battery pack, to the positive plate wire of the capacitor. Okay, now I'm going to take my 2 green wires. I'm going to pick either one of my resistors, and I'm going to hook both these green wires to the resistors, because a resistor can go in a circuit either way. It doesn't matter which direction it goes in, because it's just going to resist the current no matter which direction it moves in. And I'm going to hook one of these green wires to the other end of the capacitor, and then I'm going to use one of my knife switches. I'm going to hook the other green wire from the resistor to the one side of the knife switch, and a black wire, and the black wire, my battery pack, to the other side of my knife switch. Now that's the first half of the circuit. Can you see all that in there? All right. Now the second half of the circuit is going to have this little lamp in it, and what I'm going to do is I'm going to take this yellow wire here, and I'm going to connect it up to either side of the capacitor, it doesn't matter, and I'm going to hook this up to a knife switch that I'm going to call a light switch for reasons you'll see in just a second. Then I'm going to hook up a white wire to the other side of the knife switch, and that white wire is going to be connected to this lamp, one of the lamp leads, and the other lamp lead is going to be connected to this other white wire, which comes back to the capacitor again. Now, a good habit you ought to get into when you're building circuits is to trace out the current before you close any switches. All right? In this particular case, I've got my battery, which is the start of the current. It's going to flow down this red wire through my capacitor, through my resistor, through the switch, and back to the battery again. Now, alternatively, later on, we're going to have the current flowing through from the capacitor, through the nice switch, and through the light bulb, but you'll see that in a bit. Okay, now we already know what the voltage across the batteries are, and we're going to measure the voltage across the resistor. And I'm going to hook the red probe up to this side of the resistor, the side of the resistor connected to the capacitor, and the black probe up to the other side of the resistor. And this has been put into DC volts mode with a range of 15 volts, okay, already. And I'm all set to go. Now, simultaneously, this is part of the experiment where you're going to have two people. It's just impossible to do with one. You're going to have to read your multimeter and your clock at the same time as soon as the switch is closed. When I close this switch, this is going to be at time 0, and you read the voltage. Then every 10 seconds, you read the voltage again, and you record it in your table. Now, the second stage of the experiment, after this has already gone down to a point where you can't read it anymore because this voltage is going to be sucked out of this side of the circuit and stored in the capacitor in the form of a charge. In the second stage, what we're going to do is discharge the capacitor. My switch is open again. I'm going to connect these two clip wires together, taking the battery out of the circuit. I'm going to reverse the probes on the resistor, because now the current's going to be flowing in the opposite direction from the capacitor through the nice switch and through the resistor the other way. I'm still in voltmeter mode, but I'm going to discharge the capacitor. I close the switch, read the clock and the voltmeter at the same time every 10 seconds, and record it in the table. For the third stage of the experiment, we're going to remove our voltmeter from the resistor altogether. We're going to put our battery back in the circuit, all right, and we're going to charge up the capacitor yet again. And this time we're going to put our voltmeter on the capacitor with the red probe wire of the multi-tester connected to the positive plate of the capacitor. Got that? And we've got this, our multi-tester is still set, still set on voltmeter mode. So we close the switch again and we charge the battery, this time watching the voltage across the capacitor instead of the resistor, and then you're going to put that in your table every 10 seconds. All right? Now, discharging the capacitor the second time, instead of discharging it through the multi-tester and reading volts like we've been doing before, we're going to discharge it through this tiny lamp. Now, this switch is open, and this switch is open, but as soon as I close this switch, all the current that's been stored in my capacitor is going to go through that lamp. And so you're going to close the switch, this light switch here, and see what happens to the lamp and record your observations. Now, once all this is stored in your tables and everything like this, you're going to plot all this out and analyze your data. And I hope the questions aren't too hard. And this should be fairly easy. We'll be using a lot of this later on. See you later. Welcome to your Lab 27, Ohm's Law and Series Circuits. This mostly has to do with just resistors, all right? Everything we need, here it is. We start out over here. We have our famous multi-tester with its probe wires, and I've already connected some alligator clips of appropriate colors on the ends of these. Okay. We have all three of our battery holders, our two small ones and our large one, with 6 AA batteries total. We have our knife switch, just one this time, and we have clip wires, all the appropriate colors as described in the lab manual, and 3 resistors this time. We have a 47, 68, and 100 ohm resistors. All right, now the first thing we do this time is assemble our circuit as shown in the picture in the manual. We're going to use just one battery right off the bat, and one, well, I have one of these, nice switch. We're going to use, let's see, what color did I decide? These colors are described for you in the manual. Sometimes I don't remember which colors I use for which. What's important is that you remember where they all go. Okay. We're going to go from the battery, the knife switch, to any one of the resistors. Just pick one the first time. And where normally we would put the ammeter in this position, I think we're going to start off with our voltmeter first. So instead of an ammeter here, we're going to put this yellow wire between the resistor and the black end of the battery pack. All right? Now, we're going to take our multi-tester and we're going to put it in the circuit so that the red probe is connected to the red end of the resistor, the side of the resistor that goes through the switch and back to the battery pack, the red side of the battery pack, and the black wire on this side. Okay? Now we're going to measure the voltage across this resistor by closing the switch and reading our multimeter. So, I close the switch and watch the multimeter. The next stage of the game, we're going to disconnect the multimeter from the circuit, and we're going to move it over here. And we're going to take this yellow wire out. We're going to connect this red wire to the resistor and the black wire to the black wire of the battery. And before we close the switch, we're going to switch the multi-tester to ammeter mode, where it says 150 milli-A or MA DC, okay? So this is going to be measuring it in thousandths of amps, milliamps, all right? Now we're going to measure the current going through the circuit from the resistor to the battery when we close the circuit. So we close the circuit and then we measure where the needle goes. We open the circuit again, and then we repeat this, all right, with the resistor hooked up to another resistor in series. Now in series means that it's going to go, the current's going to flow through one resistor first, and then it's going to come around and flow through the other resistor, and then back through the rest of the circuit. We're going to measure our voltage as we did before, but this time we're going to hook up the voltmeter, in voltmeter mode, that's important, across both resistors by putting one wire on one side of one resistor and the other wire on the other side of the other resistor, and then put our yellow wire back in place again where the ammeter was. And we're going to measure the voltage across both resistors together. And then, if we move this black wire over to this resistor, we could measure the voltage across this resistor alone. If we move the whole shebang over to this resistor, we could measure the voltage across this resistor alone. And then we take out the yellow wire and put the ammeter back in ammeter mode in that position and measure the current after the current has had to go through two resistors instead of just one. Okay? You do combinations of this, and then, just for a little more excitement, this is exciting too, we're going to hook up a third resistor in series. So the current's going to go from the battery through the switch, through one resistor, through another resistor, through a third resistor, and then through the rest of the circuit. We're going to measure voltage across all three resistors, and then across each one individually. And then we're going to put it back in ammeter mode again. Take the yellow wire out. Put our ammeter in with the red wire at the end of the furthest resistor and the black clip to the battery. And we'll measure the current going through the circuit after it's had to pass through three resistors. Then we do all that again, except this time we do it with the large battery pack. And then we have a case where we want twice as many volts as we have in this one battery by itself. So what we're going to do is we're going to hook up two batteries in series by connecting the red end of one battery via this green cable to the black end of the other battery. So it goes red to black, red through circuit, back to black again. So it's as if these two batteries are together and one. This should be about 3 volts because each one of these is 1.5 volts. All right? So you repeat that with the 3 different battery combinations, with this one by itself, then these two together, and then the large battery pack, and then with all 3 resistors, and you record it all in your tables and see if you can figure out what the relationship is between voltage, current, and resistance. Now, you'll have to be reading these little stripes on these resistors to find out what the resistance of each of these resistors are, because the manufacturers, when they made them for a certain resistance. Of course, you're going to find out if that resistance is actually what it says. We're going to see if they're telling you the truth. So, I hope everything goes all right. You'll have to answer a few questions at the end of the lab, but it shouldn't be too difficult. See you next time. Welcome to your lab on parallel and series parallel circuits. This lab is almost completely the same as the last lab you did, except now we're going to be arranging the resistors a little bit differently. What we have, right down here, let's start over here. We have all of our wires as described in the lab manual. We have our knife switch, again. We're just using these two small battery holders with AA batteries this time. Those same 3 resistors we used in the last lab, and our multi-tester. All right, as before, I've already connected a red clip wire up to the red probe of the multi-tester and the black clip wire up to the black probe of the multi-tester, and I'm going to try and keep these all together and separate from each other so they don't get confusing here. Now, the first thing I'm going to do is take a yellow wire, and I'm going to connect it between the red wire of one battery holder and the black wire of the other battery holder, and I'm going to keep it there for the duration of the experiment. This is so that these two batteries will act like one big 3-volt battery. All right, because each one individually is 1.5 volts. Okay, so that's just going to stay like that for the duration of the experiment. The next thing we're going to do is we're going to take this white wire and we're going to hook it up to our little knife switch here. Okay, now this doesn't have to be white necessarily, it's just as long as there's a connection there. And then we're going to take our resistors. We're just going to take any two right off the bat, and we're going to connect wires up to one of these resistors, and another wire from the same side. We hooked this wire to that resistor to the other resistor, so that now you can see the current is going to come through the batteries, or from the batteries, through the knife switch, and then it's going to break up into 2 parts at this point and split up and go through both resistors simultaneously. And then we're going to take this other green wire, connect it back down to this resistor again, so the current will merge back together, and then from that resistor, this is going to get kind of stringy here. It's hard to see what's going on here because there are just so many wires all over the place. But if I stretch this out just a bit, maybe we'll see. We've got one resistor here and one resistor here. And got our switch over there. And we're going to take this wire and connect it up to the other end of the battery. Okay. Now, this is all set to go, except for the fact that we don't have our multi-tester in the circuit yet. Now, when we want to measure current, like we did before, we're going to take this wire out of here, and we're going to hook the red end up to the resistor, where the current's going to be coming out of, and the black end up to the battery. Oh, excuse me, we have to turn this on to we have to turn this on to ammeter mode first, because we have to turn this on really before we hook it into the circuit, because we don't want to mess up our multi-tester. Not that that will necessarily, but we just want to make sure, because these are really kind of expensive, you know. Anyway, so we're all ready to go. We're all ready to measure our current going through the circuit after it's passed through 2 resistors simultaneously. All right, so we close the switch. I'm not going to close it just now, and we read the current off the multi-tester. Now, we open the switch again, and we take our multi-tester out of the circuit, replace it with a yellow wire. All right, and then we switch the multi-tester to voltmeter mode, DC 15 volts, and we put it across one resistor, and then the other resistor, and then across both resistors, and then we switch it to ammeter mode. We put it back in the circuit, and we do the circuit again for another combination of 2 resistors, and then we get more wires and we connect all 3 of them up together. This is called in parallel because the the electrical current is going to be flowing through all 3 resistors simultaneously. We measure the current going through all 3 resistors. Then we take it apart and we measure the voltage across each resistor, and we record this all, and we see what the relationship of parallel circuits are, the resistances, the end result resistance is to the arrangement, how strong the resistors are, the voltage, etc. Okay? Now, the second half of the experiment, yes, there's more, is where we take our 2 resistors that are hooked up in parallel, and we hook them up to a 3rd resistor that's in series, as if these 2 resistors here are one resistor, and this one resistor is another resistor. And we see what the combination of having the current go through these 2 resistors simultaneously and then having to go through this 3rd resistor and then through either the ammeter or the yellow wire alternating, and then we switch it to voltmeter mode. We measure the voltage across this resistor and then across these 2 resistors simultaneously, and then we switch it to ammeter mode and measure the current coming through this resistor and through the whole circuit. And we don't have to change our batteries this time, fortunately, because this stuff, believe me, is complicated enough. But once you've gotten through this, hopefully you'll completely understand the relationship that the resistors have with the rest of the circuit when they're connected in series, in parallel, and when they're just by themselves. All right? I hope you don't have too much trouble with this lab. Welcome to your lab on magnetic fields. This lab is going to study the effects of a magnetic field coming from a magnet and the magnetic field generated by current through a wire. All the equipment you need is right in front of me. Starting over here, we'll need 3 large sheets of paper, and if they're not large sheets of paper, you can tape 4 small sheets of paper together, but you'll need ultimately 3 large sheets of paper to map out the fields on. 5 magnetic compasses, such as these, 4 or 5. Your 2 small black magnets that are in your kit. A length of about 1 foot of bare copper wire. Some electrical tape. You'll need about 5 alligator clip wires, which I've already attached between my 3 battery holders, which already all have batteries in them, and your knife switch. The box that your multi-tester came in, and as you'll see, we'll be rearranging that box a little bit. Some wire cutters may come in handy. And of course, your support apparatus and a piece of string. Now the first thing you're going to need to do with this lab is take one of your magnetic compasses and, away from any large piece of metal or any of the magnets, look and see which way the needle is pointing north for your reference, so that you know which way is north. And looking at this compass, I see that that direction is approximately north for me. The next thing we're going to do is find out which side of the magnet is north or south. Now, these magnets have north on one face and south on the other, but you don't know which face is which. Now, because these magnets are extremely strong, they're also very brittle, and so for a safety suggestion, I suggest you take these magnets and wrap electrical tape all around them like this, so that if they break, they won't splinter off and you get a bunch of little magnetic pieces all over the place. Now, take one of your magnets and stick it in a loop of string hanging from your support apparatus. And if you have an apparatus like mine, which is made up of metal poles, you want to make sure that there's a good distance between the metal poles and the magnet. Now, after the magnet stops spinning around here a little bit, after a while, it will start pointing. Well, not pointing so much, but one face of the magnet will be aiming in the general direction of north, and the other face will be pointing in the general direction of south. And if you have clever little labels that I've made similar to these, let's say N and S on them, and you know which side is which now. Because this side was facing north, I can stick my little N sticker on this one, and I know that that's the north side of that magnet. And I have a little S I can stick on this side too. And if you want to, you can do this with all of your magnets. Now, the next stage, we don't need this, so I'll set this down to the side. We're going to use about 3 of your compasses. And because a compass needle is essentially just a tiny, tiny bar magnet, we're going to see what the effects of putting one compass in the vicinity of another is. And you look and see which way the needle is pointing when it sits on the table, and you stack another one on top of it, and which direction does this needle point? And you can't really see what's going on the needle underneath it unless you kind of slide this over just a bit, and you can tell what's going on. And then you'll be stacking a third one on there, and you record your observations about the directions that the needles are pointing. All right? Now the next step of this is actually mapping out the magnetic fields of one of your magnets. All right? So we're going to take this magnet that I've labeled already, and I'm going to put it in the center of this paper. And once again, I recommend you do this in pencil, but I'm going to use a magic marker so that you can see what I'm doing here. I'm going to trace the outline of the magnet on this piece of paper. Lost my lid there. And I know which side of the magnet is north and which side of the magnet is south. And so on the paper, I'm going to label N and S for my reference, and I'm going to leave the magnet just like that. And also, I might want to write off in the corner somewhere which direction is north, and see I've already established that that direction is north. Now I'm going to take one of these compasses, and if you have a group of more than 2 or 3 people, each one of you can take a compass and do this. You can put the compass anywhere on the paper to start, and whatever direction the needle is pointing in, when it finally slows down here, okay, you put 1 dot on the paper on one side of the compass and 1 dot on the other side of the compass to represent the ends of the needle. You take the compass away and draw a line between the two, and then a little arrowhead at the end where that was green on the needle. The next step is to move the compass a little bit so that the back point of the needle is pointing toward the head of the arrow you just drew, and draw another dot and another arrow. And you can go forward continuously forever, or you can come backward, and you'll find yourself coming back toward the magnet. And you do this all over the paper until the paper is just covered with little arrows. And you'll see a pattern form which will look a little bit like a spider. And after you've done this beautiful work of art, the next stage is to take the second magnet, and when the 2 magnets pull together like this and they attract each other like these are, and I know that this is the north face, I know that this must be the south face. And so when I map out the magnetic field between these 2 magnets, I'm going to mark that this is north and south, and this is north and south on this one, and then I'm going to do the same thing with my compasses for my second map all over in between. And then for my third map, a third sheet of paper, I'm going to turn one of these around and map the field a third time. And that's all there is for these 3. Once you're through with that, you'll have some really interesting patterns. Now the second half of this lab doesn't use the magnets at all. We're going to be running current through this piece of copper wire that's going to be set up with this box. Now, see what I've done here is I've taken the lid of the box and I've moved it up and over toward the back of the box, okay, like this. And I've poked a small hole in the bottom of my box right here, and that little black circle shows you where the hole is. And I'm going to thread this copper wire through the hole. Yeah, supposedly. And when the wire comes out the other side, I'm going to bend it around the back of the box. So it's like this. And what I get is this perpendicular piece of wire coming out of the bottom of the box like this. Now what I've done with my electrical circuitry over here is I've taken all 3 of my battery holders and I put batteries in them, and I've connected them in series so that my black wire is attached to the black, and the red wire of this one's attached to this black one, and the red wire of this one's attached to this black one, and the red wire of this one's attached to my knife switch. And now I have 2 ends of a 9-volt system, and I'm going to connect the red to the top and the black to the bottom. And it's not really important which direction, but you just have to remember that current flows from the red to the black. And I'm going to have my knife switch open. And now I'm going to arrange my compasses around the needle. Around the wire that's going through the center of the box. And they should all be pretty much pointing in the same direction unless their tiny magnetic fields are interfering with each other. But as soon as I close this switch, an amazing thing will happen, and you'll have to record your observation there. And then you'll turn these around and close the switch again and see what happens to the compasses the second time. That's pretty much all there is with this lab. I hope you enjoy it, and if you read your instructions, you shouldn't have any problems. And the answers to the questions really aren't that hard in the back if you think about it. So have fun and good luck.
Hi, welcome to our lab entitled the DC Electric Motor. I think that you will find this lab to be very interesting and exciting because you will build your own working DC motor from common everyday materials. Those materials are in front of us. We have some of our plastic rulers, some of the wooden blocks, the two powerful small magnets, an unsharpened ASTS pencil, electrical tape, a little pin, a straight pin, scissors, the insulated magnet wire, a cylindrical object, sandpaper, aluminum foil, 2 paper clips, a third block, the 4 batteries in their battery pack, a red and black alligator clip wire, and finally our multi-tester. The assembly of the motor proceeds in several steps. The first step is to build the base, which I have completed here basically. Let me show some of its details. You have the 2 grooved blocks side by side. Their grooves are on the bottom, like so. You have 1 ruler on each side, and to each of the rulers on the long side, we have taped a small magnet. And these magnets are arranged so that they will attract each other. In other words, you have a north pole here and a south pole here, or vice versa. Then what you do is you take your pencil and you sharpen it just enough to get a point, like this. And then what you do is take the straight pin and you insert it at the end, like so. And if you've done everything right, it will be just of the right size to fit between the 2 yellow rulers on the base. And it should want to spin nicely like that. Okay. So that is the first stage. Now you want to build the current carrying loop. So you take the wire and the cylinder and you wrap wire around it maybe 40 or so times. And you then slide off the loop of wire very carefully so that it does not go sprawling on you when it gets free of the cylinder. And then you tape the 2 opposite sides so that you wind up with something which looks like this. In other words, you have the loop of wire, pieces of tape, and 2 pieces of wire coming off like this. Then what you do is you take the sandpaper, and by doing something like this, you can sandpaper insulation off of the ends, just maybe this much of each end, so that you have electrical contact. And to test that, you take your multimeter and you set it to the resistance measuring position, and if everything is correct, then it should read 0 when you are touching the contacts to the wires. And if that's done, then you are in good shape. So here's your loop. Then what you do is you take your pencil assembly here and you spear the loop so that you have something like this going on. Okay, so that the pencil points in the direction that the wire is going. And then what you do is you take this thing and you bend it into a square-shaped loop, from a round loop to a square loop. And then you install it here and make sure that it's still balanced. It should look something like this. If it is not symmetrical, if it's not balanced, if it does not clear the magnets, then you should make some suitable adjustments. But everything should work basically like that. And if you've done that, that's great. Then you have to insert the commutator. To do that, you take some aluminum foil, you cut it to the proper size, and then you attach that in the manner described to the pointed end of the pencil. And when you're finished, then everything should look like this. Notice what I have. I have a section of aluminum foil right here, then I rotate it, and then there's a gap of white, and then another strip of aluminum foil, and then another gap of white. So these two strips are right next to each other, but they are never in electrical contact. And you wrap electrical tape top and bottom to make sure they stay nice and securely fastened. Then the last stage is to take the two free ends of the wire, which are right here, and you take those two free ends and you connect them to where the foil part is, so you wind up with something like this. So here's one loop of wire, and it connects to this side, and the other loop connects to this side. And you notice that the white gaps here are, you can see them when the coil is flat. So here you see silver, there you see the white gap, here you see silver and the white gap. So that orientation is important. So here's your finished gizmo. Okay, so it looks like this. And to see that everything is working fine, you should again test for electrical continuity by connecting the probes to the opposite foil strips, which are called the commutator. And if everything is good, it should read 0. And if that works, then you know this piece is mechanically and electrically reliable. The final step is to make the brushes. So to do that, you take this assembly here, and it should go in place something like this. Okay? And then you take these clips and you bend them into an L shape like this. So you have one, and you do the same thing with the other one. And then what you do is you tape them into position. First you have to, of course, get this thing into place, and you fix it so that the foil and the split ring commutator is over the high block. So that is quite important. Okay? Then what you do is you tape the brushes into position like this. You want them so that the L-shaped base points down the axis of the pencil. In other words, you want them to be able to go flippy-flop like this. And you do the same thing for the other one. So the point is, each paper clip touches one side of the commutator at a time, and they do not touch each other. Okay? And now we're ready to see if the thing works, because the assembly is basically complete. You may want to insert a reinforcing bar like this, or you may not. It just depends on how things work for your device. Okay. So the last thing now is you have your battery pack, and you supply current to the two brushes. So you clip one here and one here. Make sure the clips do not touch each other. And voila! Oh, this thing just leapt into life. Here we go. And you can see that this is quite a fast little motor there. And so I hope you have fun building this thing.